Hi, welcome to the video for our paper. The paper is about the symmetric Ising perceptron in something called the frozen 1 RSB structure. And this paper is joint work with Changji Zhu from Harvard. So what I would like to do is introduce you to the perceptron model, give some of the history, some of the conjectures and results around the model. I think it's a really nice model, both mathematically and from a computer science or even statistical physics point of view. It was invented as a toy model of a neural network, and I'll describe in what way that is. And there's some nice analogies to be made between this model and random constraint satisfaction problems, like random KSAT. And I'll describe analogies both in results and in techniques. The big open problems related to this model relate to algorithms, learning algorithms, and when can we expect there to be efficient algorithms to find solutions in high dimensional problems. And this is a nice toy model to test some of these algorithms or algorithmic ideas. And finally, the main results of this paper are some new structural results, proving something called frozen 1 RSB behavior. And I'll discuss the results, a little bit about the proofs, and discuss how they're related to algorithmic questions. Okay, so to begin with, I want to start with a very nice and natural problem in geometric probability. We have a sphere in n dimensions, and the question is, how many random hemispheres, uniformly random hemispheres, does it take, typically, say, to cover the sphere? Okay, and it turns out this problem has an exact answer, and it was given by Wendell and cover of information theory fame. And the exact formula is as follows. The probability that the sphere is covered by m random hemispheres is given by this exact formula. Okay, you can digest that formula, but what you'll see is that this probability is exactly 1/2 when the number of hemispheres is twice the dimension. Okay, so somehow m equals twice n, the dimension, marks some transition between it being unlikely or likely to cover the sphere. Okay, and if you do a little asymptotic analysis and think about as the dimension n tends to infinity, then you get the following sharp threshold result and scaling window. If m is a little bit bigger than 2n, then with high probability, as n goes to infinity, the whole sphere is covered. And if m is less than 1 minus epsilon 2n, then with high probability, the sphere is not covered. There's uncovered points on the sphere. And from this formula, you can even read off the scaling window. So how many hemispheres do you need to add to send the probability of coverage from epsilon to 1 minus epsilon? That's on the order of square root n. And if you know about random constraint satisfaction problems, you'll know that we basically know no results about scaling windows there. And so this is really a special problem here, this hemisphere coverage problem. Okay, you can immediately think of ways to generalize that geometric probability question. The previous one is just a special case of something called the spherical perceptron. And here's the model. You have some parameter kappa, that's a real number, and you pick MIID standard Gaussian vectors of dimension m, dimension n, m vectors of dimension n, and define sigma. And I'll think of this as the solution space as the talk goes on. Sigma is all the vectors on the unit sphere whose dot product with each of the xi's is at most kappa. Okay, so the previous example was just kappa equals 0. And you can think of this is a set of all points on the unit sphere that are not covered by a certain random spherical caps. And these caps are defined by both kappa and the randomness, the disorder given by the xi's. And so the first question you can ask, given these parameters, the dimension, the number of caps, kappa, is the solution space typically empty or non-empty? Okay, and as I said, the special case was kappa equals 0, and kappa being negative or positive actually makes quite a big difference because it determines whether this sigma is a convex set or not. And so the techniques and our results really depend on this in the spherical perceptron case. Okay, so moving closer to computer science and algorithms, you can come up with other variants, and this one makes a lot of sense, the Ising perceptron. And now instead of solutions lying on the sphere in n dimensions, solutions are plus minus 1 vectors of dimension n, so the Hamming cube in dimension n. And we still have Gaussian vectors, disordered vectors. And so now this solution space is the set of all Hamming vectors of length n, whose pairwise dot product with the disorder is at most kappa square root n. Okay, I have to have that square root n because I haven't normalized the Hamming cube to have length 1. And again, the question is, for what values of n, m, kappa is the solution space typically empty or non-empty? Okay, so these are two really, they're similar models, but have significant differences, the spherical perceptron and the Ising perceptron. And the adjective describes what form the solutions take. I'll say that whether the constraint vectors, these xi's, are Gaussian or plus minus 1 vectors, that doesn't really matter. Okay, so you can choose either one, and at least for the known results, this choice won't matter. So spherical, we're talking about a set of solutions, Ising, Hamming cube solutions. Okay, what does this have to do with a neural network? Well, this Ising perceptron was first studied in statistical physics by Elizabeth Gardner in particular, as a simple model of a one-layer neural network. These Gaussian vectors were patterns to be stored, and you say you store these vectors if you find a set of weights, y, on the Hamming cube, that is consistent with every single pattern. And so the question is, how many IID random patterns can be stored? This is exactly the question of when do there exist solutions, when is sigma non-empty? And this threshold is called the storage capacity. And so instead of thinking this threshold for emptiness or non-emptiness in the literature is the storage capacity because of this initial motivation for neural networks. Okay, but you know, taking a different perspective, you can think of this as a kind of random constraint satisfaction problem. To remind you about random CSPs, the classic model is random K-sat. Here we choose m uniformly random K clauses on n Boolean variables. So if K is 3, a clause might look like x11 or not x7 or x12. So it has width K. And a solution in the Hamming cube is, it's a solution if it satisfies all m clauses. Another way to say this is each random clause rules out a 2 to the minus k fraction of all possible solutions because there's exactly one setting of the k variables that is unsatisfied. And we want to know how many random clauses we can add and still have a non-empty solution space. Okay, so the Ising, you can translate the Ising perceptron to this perspective. Each Hamming vector y is a potential solution, each xi is a constraint, and a vector y satisfies the constraint if the pairwise dot product is at most kappa square root n. And again, because we've chosen the scaling kappa square root n, each constraint rules out a constant fraction of all possible solutions. And we want to know how many random constraints we can add and still have solutions. So really it is a very similar setting. And now the storage capacity corresponds exactly to the satisfiability threshold. Okay, so what is at least predicted in the literature about this model? So Krauth and Mazard, following the work of Gardner, gave a prediction for this threshold, satisfiability threshold or storage capacity based on the non-rigorous replica cavity method, replica symmetric cavity method. And for kappa equals 0, the prediction, okay, it's some decimal expansion, but it's about 0.83. And the conjecture that the model is replica symmetric for all densities below this critical capacity. And this is different than in the spherical case when you can get replica symmetry breaking. So what is known about this? It turns out that Jian Ding and Nike Sun recently proved the lower bound. So proved that this predicted threshold is actually a lower bound on the satisfiability threshold. using a very sophisticated second moment argument with complicated conditioning argument, it turns out that the upper bound is still open. So it's not so easy to do the types of upper bounds that are used in random CSPs. And so unlike the case of random CSPs, where usually the upper bound comes first and then the lower bound is the harder argument, here the lower bound is known, but the upper bound is still open. But Krath and Mazar predicted much more than just this threshold. They predicted something about the solution space. And so remember, solution space is the sigma, which is the number of solutions. And this, this will decrease, the set of possible solutions will get smaller and smaller as we add more constraints. And what they predicted was that with high probability over the choice of the instance, the disorder, the xi's, and the choice of a uniformly random solution in the solution space, the cluster, the solutions nearby, connected in the Hamming metric, actually has vanishing entropy density. So it's e to the little o n, not exponential size as in many random CSPs. There were even stronger conjectures made in the physics literature where they conjectured, in fact, that with high probability solutions, typical solutions, are completely isolated. There's no nearby solution at even linear Hamming distance. And we would say solutions are completely frozen. And this is called the frozen 1 RSB picture. The next question might be algorithms. Are there algorithms to find solutions given the instance? Kim and Roche, improving some lower bound, actually gave an algorithmic lower bound, and they gave an algorithm to find solutions at very small densities. And you can likely modify, say, discrepancy minimization algorithms to find solutions at very small densities as well. But some other statistical physicists made some very bold conjectures about algorithms here. They conjectured that, in fact, good algorithms, so algorithms that are efficient at finding solutions at higher densities, do exist, but these algorithms, and they gave some proposed algorithms, they find solutions that, unlike most solutions, are not isolated. They lie in some exponentially rare clusters of positive entropy density. So exponentially large clusters, but if you look at all of these rare clusters together, they're still an exponentially small fraction of the total number of solutions. So this is a really bold prediction, because it says that if you just think about the equilibrium picture of the model, so if we think about just picking a random instance and picking a random solution, we think of this as telling us a lot about the model, the probabilistic behavior of the model, and maybe the algorithmic behavior of the model. But what this conjecture here is saying is that this is actually not telling us the important algorithmic information, and exponentially rare parts of the equilibrium picture are actually what matter for algorithms. And so I find this a really fascinating and somewhat frightening conjecture. It means that a lot of the work that we've been doing as mathematicians might not be related to algorithms at all. And so we really should try to figure out if they are correct here or not. Yeah, this is what I say. Okay, so how are we going to study this? So, as you can see, because we can't even do a first moment upper bound on the capacity for the Ising perceptron, it's a rather difficult model. It turns out there's this, we can introduce a simpler model that should have all the qualitative features of the Ising perceptron, but might be more amenable to proving theorems about. And that's the symmetric Ising perceptron. And this is really closely related to the problem of discrepancy minimization. It has symmetric constraints. So we have the same Gaussian vectors as our disorder. And now the solution space is all Hamming cube vectors, for which the absolute value of the inner product with each constraint is at most kappa square root n. And so this is the symmetry, taking the absolute value. And so now we can think of constraints as opposed to being hyperplanes that cut off some fraction of the hypercube, they're parallel hyperplanes that cut off everything outside. Okay, so this symmetrization can really help. It was introduced in a paper I had with Benjamin Albin and Lenka Zdeborova. It's an analog of random K not all equal set. And not all equal set is when you forbid the all true configuration and the all false configuration. This gives some symmetry to the model. In particular, if you have a solution, then the negation of the solution is also a solution. The same thing with the symmetric Ising perceptron. And this should make analysis easier. And in fact, it does. The result we proved in this paper with Benjamin and Lenka was that we can find the critical capacity. So, okay, there's some condition. I'll tell you what the condition is. It's some assumption, but subject to this assumption, the critical capacity of the symmetric Ising perceptron is just given by this formula. This is actually, all it is the first moment threshold. So you can compute the first moment expected number of solutions, and this is the threshold at which that expected number is 1, say, and when you're above this threshold, the expected number of solutions goes to 0. It turns out this is tight, so we can do a second moment argument to prove this. So the one-line proof is first and second moment methods work. Okay, so here is, what is this? This is showing the second moment works in a picture. This is the plot of 1/m log expected number of pairs of satisfying assignments, solutions, as a function of overlap of the two solutions. So beta is the overlap, like 1/2 is uncorrelated here. And as usual with the second moment argument, the second moment will work if the maximum is achieved at 1/2. What's interesting here with the picture, so in the same sort of thing happens with random not all equal set, except the picture looks different there. The second moment curves look like this. So here's 1, here's 0. They go up and then down and then up, and then we ask, does the max hit there? So the second moment is not tight for not all equal set, because as you get near the threshold, these little bumps around 1 and 0 actually become the global max. Here, the curve goes down with actually infinitely negative derivative there. And so it turns out as long as, the max, as long as we're below the first moment bound, the max is always at 1/2. Okay, the assumption we make is that this curve only has 3 critical points. Okay, so it looks obvious, but I don't know how to prove that. But that's the picture. And this picture actually tells us a lot more, and that's where the current results come in. So here's the main result of the paper that I'm presenting today with Chengji Zhu. So subject to the same assumption, for any alpha greater than 0 and below the critical capacity in the symmetric Ising perceptron, with high probability over the choice of the instance and the choice of a solution from the solution space, the solution is completely isolated. That means the nearest other solution is at linear Hamming distance. So the solution space is completely frozen. And note the quantifiers. It's with high probability of the choice of the instance and with high probability of the choice of random solution. So it doesn't mean that every solution is isolated. It means that a 1 - little o1 fraction of solutions are isolated. And so this proves, at least for this model, this proves the conjectures from the physicists, but it doesn't contradict this algorithmic prediction that there are exponentially rare clustered solutions. And how does the proof go? The proof is to use the planted model. Okay, so let me just say a few words. So the planted model is where we pick a solution to start with, and then we only pick constraints consistent with that particular solution. It turns out the second moment curve also gives the expected perspective of the planted solution in the planted model. And so because this curve goes down at the start, it's saying that in the expectation, there are very few solutions close to the planted solution. Okay, and that's actually not such a bad calculation. So in the planted model, calculate the expected number of other solutions at Hamming distance at most epsilon n. And we can show that tends to 0. But now you have to have some argument to say that the planted model says anything about typical solutions. So what does that tell us about the usual model? Okay, and we use techniques from the random CSP literature. So the takeaway message is, if the number of solutions X is concentrated, then the following two experiments are close. Okay, and how concentrated and how close, these are related to each other. But the first experiment is the planted model. Pick a solution uniformly at random, and then pick x1 up to xm with sigma as the planted solution. The second experiment is pick your disorder at random, and then pick your solution uniformly from the solution space, conditioned on the event that it's not empty. Okay, and so that's not a bad conditioning if we're below the satisfiability threshold. And the probability of so the probability of oops, that's not what I want to say. I was correct. The probability of picking a given instance, okay, a given set of x's, is proportional to the number of solutions. And so if the number of solutions for a random instance is tightly concentrated, then instances in experiment 1 are close to uniform, and these two experiments are close together, and we can transfer information. Okay, and so our main technical result in the paper is a concentration result. So for alpha less than alpha critical, if we look at the log of the solution size, the size of the solution space divided by n, well, it's the expected size plus some error term that's like log n over n, okay, that tends to 0. This is just the expected size of the solution space, which is easy to calculate. And okay, so this is probably the interesting technical part of the paper. It goes by a martingale argument. So we have some inductive hypothesis about how two random samples from the solution space at a certain step in the process are nearly orthogonal with high probability, and somehow we can use this inductively. Okay, so that's basically what I want to say about this paper. I'll remark that subsequent to our paper, even stronger result on concentration was proved. So by Abe, Lee, and Sly, they proved a conjecture from our work. And our conjecture was that, in fact, the below alpha critical, the random model and the planted model are contiguous. There's a much stronger notion of closeness than we proved. And they, in fact, did prove this. They proved that these models are mutually contiguous, and in fact, they gave they determined the limiting distribution of the number of solutions. Quite an interesting argument. They proved it using some adaptation of the small subgraph conditioning method, where we use this new martingale argument. Okay, so finally, let me remark on some open questions. I think the main open question is to understand these potential clusters of exponentially rare clusters of exponential size. So do these clusters exist? Do they exist? At what densities do they exist? And can we design algorithms to find them? So the Kim-Roche algorithm, in fact, does show that these clusters exist, but at very small alpha. We'd like to know at how large an alpha do you still find these rare clusters? In particular, can we show that there's some interval where these rare clusters don't even exist? Of course, the algorithmic problem, at what densities is there an algorithm to either find a solution in the standard model or find the planted solution in the planted model? These are nice algorithmic questions. And then the main question is to understand this algorithmic conjecture by the physicists. In this or in other models, can we design algorithms that work for wider ranges of parameters by searching specifically for out of equilibrium solutions? So solutions that are not typical. This really would call into question a lot of arguments we make about the typical solutions explaining algorithmic barriers. So maybe the answer is no, maybe it's yes, but I think this is a really important question to look at. Finally, okay, a scaling window. It'd be great to understand the scaling window in this or other random CSPs. Okay, thank you for tuning in. That is it.